welcome to GemChem. Now today's video is on coordination chemistry part 10 video, and here we are going to deal with counting of electrons in complexes by neutral method. Now before starting, already 9 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to GemChem, don't forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So we are going to deal with 3 types of ligands. One is terminal ligand, next anionic ligand, and the last one will be bridging ligand. When we are talking about carbonyls, then each carbonyl ligand donates 2 electrons, whereas when we are talking about thiocarbonyl ligands, each of these donates 2 electrons. Similarly, for hydrogen as a molecule, it is going to donate 2 electrons to a particular metal like this. Here we have a metal and we have a hydrogen-hydrogen bond. So the 2 electrons present in the hydrogen-hydrogen bond will be donated. In case of alkene as well as alkyne, 2 electrons will be donated. If you consider alkynes, then we can say that there can be donation of 4 electrons. But this is not possible because another pi orbital which is present is perpendicular to the axis of the metal. Thus, the bond formation with that pi orbital is difficult. So, only one pi actually takes part in the reaction. Next, we have our amines, then amino group, NH3 and water. Both using their lone pairs donate, so they are having an electron count of 2. Similarly, for N2 also, we have an electron count of 2. For bipyridine, we have also 2. Orthophene or PAP, when we are considering, there is 2 plus 2 donation center. As a result, the total comes to be as 4. When we are considering nitrosyl group, it can bind in 2 ways. One in which the metal binds to the nitrosyl directly in a linear fashion, that is one single bond, double bond oxygen. This is the way. In this case, it has an electron count of 3, whereas when we are considering a bent nitrosyl, where your metal is connecting in a bent fashion with the NO, then in that case the electron count comes to be as 1. Now when we shift for anionic ligands, if you consider X minus, in that case electron count is 1. Similarly, for sulfide and oxide it is 2. For N3 minus, that is nitride, it is 3. Carbene and carbine. In these cases, for carbene, if we consider the bond is like this, metal, then we have double bond Cr2, whereas for carbine we have metal, 3 bonds, and then we have Cr. So in this case, 1 each electron from each bond is being donated to the metal, as a result of which electron count becomes 3. When we are considering our next portion, that is our cyclopentadienyl. As we have already seen that cyclopentadienyl can bond in 3 ways. One in which only a center is bonded to metal. Another in which case one center is bonded to metal as well as one double bond participates. This becomes eta 3 and the electron count becomes 3. When we consider the cyclopentadienyl participating with all its double bond, that is 2 double bond and 1 end, that is minus charge, then it becomes eta 5 and the electron count becomes 5. Now we are going to shift for the last one, that is allyl. In this case we have allyl bond, so this is allyl. When it is bonding with this center, it is eta 1. When it is bonding with this center as well as the double bond, it becomes eta 3. 2 electrons come from the double bond and 1 electron come from this end. Now we are going to see how the bridging ligands have their electron count. So when we are considering halide, so halides are bridged together in between, as a result of which when we draw it like this, metal, we have chlorine here, we have metal here. So here the 2 electrons are being donated completely and 1 electron is being donated to this metal. Others are your rest pairs of electrons in case of your Cl minus. Similarly, for OH minus also, we will have the electron count as 3. So let us see how it is occurring. Now see here, you have oxygen. 1 electron is bonded with the hydrogen. You have the electrons like this. So total 2 electrons are being donated to the metal, whereas one of the electrons present here along with this electron comes with metal. So one metal is connecting with the 2 electrons which is fully present in the oxygen. Another metal is connecting with one excess electron which is present in OH minus and one electron which is already present in OH. So here the electron count becomes 1 from here and 2 from here. So we have the count as 3. Next we shift for our H minus ligand. So this is also a bridging ligand. When we are talking about this, we have H here and we have an electron of hydrogen itself and an excess electron, and it is participating in the bond formation. But since hydrogen has the capacity of 1 electron of itself and it is taking up 1 excess electron, actually we can consider that the electron count for hydrogen will be 1 electron only. When alkyne is considered as your bridging ligand, then we can see that this count becomes 4. The reason for this count to become 4 is that the 2 perpendicular orbitals which makes the pi bond are away from each other and the 2 different metals are actually bonding. So we can see that 2 plus 2 electron count is being observed. Now using these all things, we are going to see the application of 18 electron rule. Now first question is, using 18 electron rule you have to explain whether the following complex is stable or not. So in that case our first complex is MnCH3CO5. So when we are considering manganese, then manganese has electron count of 7 electron at the outermost shell. When we are considering alkyl group CH3 minus, it has an electron count of 1 electron. And when we have 5CO, we have already seen CO has 2 electron donation capacity according to the electron count, and when we add all this up, we get 18 electron, and we know when we are coming up with 18 electron, this complex is actually stable complex, right? Next complex we see here is our osmium 3 carbonyl 12 in number. So always remember, when there is multiple metal center, then we assume that there is possibility of maximum number of metal-metal bond formation. Now when we are considering osmium 3 carbonyl 12, then in that case for 3 osmium we have our 3 into 8 electrons to produce 24 electrons. Whereas in case of carbonyl we have 12 carbonyl, as a result of which 12 into 2 we get it 24 electrons, right? Similarly, since I have already told you that we are going to consider maximum number of metal-metal bond, so we will have 3 osmium-osmium bond. As a result, each metal-metal bond will contribute to your 2 electrons, and we are going to get 6 electron. So total we are getting 54 electron for 3 osmium. So for 1 osmium we are going to get 18 electron. Thus we can say that this complex is also a stable complex, right? Now we are going to see another type of question. So in that case, first we have to know the basis of 18 electron rule. So why we are always saying that 18 electron rule is compulsory? Because the bonding molecular orbital in case of octahedral complex can accommodate a maximum of 18 electrons, and if we are having 18 outer electrons in the bonding orbital, then the bond order will also be maximum, and we always know that when the bond order is increasing, the stabilization will be maximum. But is it always true? No, actually not. When we are considering square planar complexes, maximum 16 electron accommodation is being possible. Like platinum 2, palladium 2, iridium 1, they can form square planar complex. So one of the examples where there is importance of 16 electron rule, we can see if you write down eta 3 C3H5 palladium, Br2 palladium, similarly eta 3 C3H5 and if we close it, then we have this one, this structure, then palladium, and we have Br as our bridging ligand, and finally same thing is being repeated in the opposite side, and we have this structure, right? So in this case, if we calculate for 2pd, we have 2 into 10, that is 20 electrons. Similarly, for 2 mu Br minus, we have 2 into 3 electrons, as we have already seen, bridging ligand for bromide, we have 3 electron donation, and for eta 3C3H5, there are also 3 electron donation, as a result of which this also becomes 2 into 3 electron, which is your 6 electron. Now when we add it up, we get 32 electron for 2 palladium. Now if we divide it by 2, we will get 16 electron for 1 palladium. So we have now seen that for square planar complex, we need 16 electrons to make the structure stable, right? Now we are going to see how to find the values of X and Y in the following complexes using 18 electron rule. So for this case, we have 2 cobalt, right? So we have 2 into 9 electron, which is 18 electron. Similarly, we do not know the number of CO. So we are considering X into 2 electron to be as 2x electron. Next we have eta 2C2H2, which we very well know that 2 electron donation, and the last is 1 cobalt-cobalt bond. This will donate you 2 electron. So total comes to be as 20 plus 2x, and this stands for 2 cobalt, right? So finally this should be equal to your 2 into 18 electrons, right? For the 2 centers you should have 2 into 18 electrons. So once you solve this, you are going to get x equals to 18 minus 11, which is equals to 7. So your value of x comes to be as 7. This is the simplest method to find out x and y in a given complex using 18 electron rule. This is our next question, where we have to calculate or find the number of metal-metal bonds that are present in the given complex. So in that case, if you are considering, first take out the electron count. For 4 osmium, we have 4 into 8 electron, which is equals to your 32 electron. Similarly, for 15 CO carbonyl, we have 15 into 2 electron, which is your 30 electron. Next, we have X number of metal-metal bond, and we know metal-metal bond donation is 2 electron, so 2x electron. Then add it up, you are going to get a total of 32, 30 and 2x. This total will come to be equal to as 4 into 18 electrons, because we know that 4 centers, so each center is having 18 electron. Once you solve this, your x comes to be as 5. So this is your answer. There will be 5 metal-metal bond. Now we are going to see another type and the last type of question, that is, what will be the molecular formula of compound containing, in this case this will be your CO, that is carbonyl. This is wrong. So if we are considering these, we are always assuming that this is a mononuclear complex. So we don't know its value or this one's value or your carbonyl's value. So we are going to take it as XYZ. So for iron we have 8 electron. Now for carbonyl we can consider X number of carbonyls. So we have 2x electrons. Similarly, for eta 1C5H5, we don't know the value. So we are considering Y. For eta 5C5H5, also we don't know the value. So 5 electron donation into Z. So our total should come to be as 18 electron. We have 8 plus 2x plus Y plus 5Z is equals to 18. So we have our equation 2x plus y plus 5z equals to 10. And the simplest method is trial and error method. And always remember that eta 5 can be considered as 1. So you can take Z1. Now assume such a value of x and y so that the answer comes to be as 5. So we can easily consider y as 1 also and x as 2. Another solution can be like if you consider x as your 1, y as 3, z as 1. So there can be more than one probable solution, but what you get is this one is the most stable, because as we know that eta 5 and eta 1, 1 is suitable. If there is 3 eta 1, it is better to have a eta 5 at that case, as a result of which this answer is more appropriate. Now this is your checkpoint. Take screenshot, and we are going to discuss the checkpoint of part 7 as well as part 10 in 2 separate videos. So this is first page of checkpoint and this is the ending page of checkpoint. So in the next video of coordination chemistry, we are going to deal with valence bond theory, and also we are going to discuss the checkpoint answers. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.